Ladies and gentlemen, this technical break was really short, thanks to our great technical support. It's now my great pleasure to welcome you to this even more discussion-oriented, even more in-depth oriented to the topic, this workshop on the machine learning, model predictive control combined together. It's my great pleasure that I found these two guys who were really willing to come here and share with us their thoughts, their applications, their implementations, their evaluations of the different control strategies. I'm not going to spoil too much, don't worry. Let me just say, we have here Professor Johannes Jaschke and Turan from NTNU Trondheim from Norway. Johannes, he graduated from RWTH Aachen from mechanical engineering, and then he did his PhD in Norway, in Trondheim, at NTNU in chemical engineering. Evren, well, forgot to say, you had some positions at the Carnegie Mellon and NTNU, and he's now a professor. Evren graduated. He's maybe one of the farthest participants by the origin. Well, we have to count it. So he graduated in chemical engineering at the University of Cape Town, and he's pursuing the PhD in Trondheim with Johannes' supervision. They both work on the topics of the workshop, and I just said enough probably, and I give a word to you.
Okay, so thank you very much, Rado, for inviting us here. So actually the title of the workshop is Strategies for Efficient and Robust Model Predictive Control. And when Rado asked us to do that, I said, what should we do? What do you want? And he said, you can do what you want. So so this is what we're doing. We have Evren and myself. We have been planning this workshop. So we had a very nice introduction already of myself. I think you said everything. I work a lot in oil and gas production and green hydrogen, and with MPC and estimation and these things. And then maybe the most credit should go to Evren. He's been working hard, working on the simulations and on the slides and discussing. I think that's us. So when it comes to the workshop, we will first have a short introduction to MPC, just to have to get on the same to have the same basis, and then we're going to speed up a bit talk a bit about speeding up MPC, and then later also taking into account uncertainty in a systematic way, and finish with some outlook and challenges in this afternoon. The material that we selected is based on what we thought would be interesting, what we were curious about to learn more about. And so what we're presenting here is a snapshot of what we know. And also, as it is a workshop, we would like to have it interactive. So if you have questions, comments, or thoughts, or if you have different experience, or just something to add, we would be very happy if you could just chip in and say, yeah, we've been working on this and we can confirm this, or actually this is not the way we see it. Please don't be shy. I think then the work, like everybody can get more out of this workshop. So just to get on the same level, like machine MPC. So in a picture, MPC is we having it's model predictive control. We're having the past where our process is coming from. We have some output, and we have a reference trajectory, and we want to make sure that our output matches where we want to be. And to do that in MPC, we predict the future. We predict how we have a model that tells us how our process is going to behave in the future, and then we solve an optimization problem to make our process behave such that we end up reaching the reference trajectory unsatisfying constraint. So we have a prediction horizon. We typically predict a while into the future, as far as we can. So where is MPC actually in the industrial control landscape when we set it up? Well, so usually we have this hierarchical timescale decomposition of the control structure, and it seems like MPC has been applied almost everywhere. So from explicit MPC with like milliseconds sampling time to real-time optimization, where you have like sampling times of maybe minutes or hours. And the setting that we're going to be looking at here in this course is a setting where we have a plant. Our plant gives us measurements, and from these measurements we will sometimes need to do estimation. We need to estimate the states. Where is our process currently? And then this estimates where we are. That is going to go into some target selector, or for example, we need to find out what is it that we want to do. And then it goes into the controller that calculates the inputs. So so the set points come from the target selector. This target selector could also be an operator. We have the control variable u, or the input to the plant, and the plant measurements. So we're going to not focus so much on this estimation part, or not at all actually. We're going to assume that we get this here, and it might be good or it might be bad, but we have some kind of estimate. So how does this then work if we want to predict the future and we do MPC? So this is kind of run iteratively at different sample times, and then it can look something like this. So we are here right now, time k, and then we take our model, we predict the future, we optimize it and find what is the best input for the future, and then this is this one. So we have all the inputs into the future, and then what we do is we take the first input, we implement that, and then because our knowledge about the future is not perfect, we do the same thing again. So we wait when our plant is here, we get a new measurement, then we predict again, we find a new input, we implement it, and so on. So we keep doing that over and over again. And so this sampling time here, that can be very short if you can optimize fast enough. Typically we want to have it short, but then it can be hard to solve optimization problems. So, but we have heard several presentations about this also in this conference about, for example, explicit MPC. We'll get also back to that later in this course. Okay. So in practice, this computational time that we need from getting the measurement to being able to calculate the input might not be negligible. So we might actually have to do something about that. We have to do something smart about it, because it's very easy to set up big optimization problems that you then have difficulty solving. So also part of what we're going to present today is about actually how can we make sure that we don't have a delay, or that we have minimal delay between getting our measurement and then implementing the new input. Otherwise, we're acting on outdated information. Okay, so why has MPC been proposed? What is that good for? It's especially good if you have constraints that are changing to handle them. Also to improve operating efficiency. And conceptually, it's simple. You have a model that tells you the future. You can play with the model to find out what is the best strategy, and then you implement that. So that on that level, it's very, very simple. So already in '89, like it was mentioned, that the flexible constraint handling capabilities of MPC, they are an advantage. And then in 2000, Main, they say that actually, or he formulates it a bit differently, but like the ability to handle control problems where offline computation of a control law is difficult or impossible. So if it's not so easy to express it simply, the control law, that's when MPC has been successful. So what goes into the MPC? The first thing is an objective. We need to find out what is this controller, what should it do, and that alone can be difficult to find out if you go in practice onto a plant and you talk to operators. It's not so easy to put all the desires that they have into this one objective. So you have like the prediction horizon. You have a model that tells you the future. It can be continuous or discrete time. We have a prediction horizon. So typically we pick some large n, as large as we can. Or some special cases you can even have a prediction horizon of infinity. And then we have the constraints for the operation. This is what our plant needs to be satisfying, so we write them like this. And then often for stability, we also have some time, some finite time constraint that says that at the end of the horizon, don't do something stupid. So don't blow up the plant when the prediction horizon has ended. Yeah. And then we'll also need an optimizer. We need something. So once we have set up this problem, we're going to solve that. So these are different ingredients that we need. So for the the key thing that we will have here is the model. Like based on that model, we'll take decisions, and if we're well informed, we'll take good decisions. If we're bad informed, we'll take poor decisions. So it can be continuous or discrete. We can either get it from physical insight, like we have seen very nicely in the previous presentation, or we could also just use data to find out. And most industrial MPC actually uses linear models, so they look or can be written in some form like this, which are linear. And the reason is because they are easy to solve reliably. So the model then requires the system state as an input. We need to know where are we now in order to find out where we're going to go to the future. And there's also different types of models. Some models are in state. Others, they don't have state. They just have outputs. So they don't have the state part. So they just have outputs. So once we have a model, we can find out what is it that we want to do with that MPC. So a very common goal is we want to get some variables to some target. So some set point, we have some quality, some composition that we want to have at that quality so that we can sell it. And often the stage cost then has two components. It is like this, what we call the stage cost. That is for every time point summed up, and then we have it often, so it's 0 if we are at our set point. And then we have a terminal penalty, which is also helping us that we don't do something stupid at the end of the horizon. So most common in usage is to have a quadratic objective, something like this, and also a terminal penalty that is also quadratic. Why it's like that? I think it's practical to solve. And maybe you can also make some nice statistics from that. But we'll not go so much into detail into this. So recently, we have also seen a lot more the economic cost, which is maybe the true power that you could think this MPC can have, where you, instead of tracking a set point for some product, you put the economics right in there, and then you optimize that. So that can be production, throughput, maximizing throughput, or minimizing energy usage, emissions. So you can put them all in there, and this all works into this framework. You have a model, and you have an objective function. You optimize that together. And then you have the constraints. So that is like the state, and that can be operating constraints for safety. That can be pressures, or it can also like be hard limits on inputs, like the valve cannot open more than 100%. We have these terminal constraints that, again, at the end of the horizon, that you don't do something stupid. And a lot of these constraints here actually are tuning parameters in practice. So when you implement it in practice, these are tuning parameters. You need to find out how you actually set them. For feasibility, it can be necessary maybe not to apply state constraints or to make them soft constraints, to weaken them, and then to have a backoff. You can write this also like compact like this. So then, like this prediction horizon, how far should we look into the future? We could say, let's just not look into the future at all. Let's just set n equals 0. That would be a very easy optimization problem to solve. You could have a very fast sample time. And you ignore the future, but that typically is giving very poor performance. So that doesn't work. We would like to have something long, but then as our prediction horizon gets long, we also have a very large optimization problem, a big problem that is difficult to solve, that we cannot solve fast enough. So there's some trade-off there. So in some special cases, actually, you can you can have like an infinite horizon, and then you can find an analytic solution. So if you have a linear model and a quadratic cost, then you can find that, and no constraints, then you can find, it's called this LQR. But in general, if there's constraints, then it's hard to write this feedback law analytically, and then we use MPC. So then, like if we have a linear MPC problem, then we have like this. Typically, when people say linear MPC, they have a quadratic cost function that penalizes the states and also the inputs. We have a terminal cost. We have the model. The constraints are typically polytopic. And yeah, and then we can also have the outputs there. So this has been used, or this type or similar types are used maybe most, because also they can be solved most reliably and fast. So it's a quadratic, it's a QP. So the optimizer, that is maybe the motor or the engine. So with these linear MPCs, they can be solved quite fast. You can get guaranteed solved. If you have a nonlinear model, things get more difficult. It depends on what kind of starting point you guess. But they still can be solved reasonably well with modern algorithms and computers, but it's hard to make guarantees. And they can still take a lot of time. So we will be talking about increasing the speed of MPC. How can we actually make it faster? So yeah, this is maybe just a rough kind of setting where we are, where we're starting from. So at each of these journey, we solve this dynamic optimization problem, and we want to solve it fast enough so that we don't act on outdated information, because it has been shown that if you wait too long before you do something, you can get instability, so that the controller might not give you what you want, even though the optimization problem is always nice, but if you implement it in closed loop, it's not going to work. And then we take the first input, and we put that into the plant. So this is maybe the general setting. Before I just continue a bit about how we can make this solutions faster, here is, we put some reference here that you can look up for more details that we used. If there's any questions or comments, then now is a good time.
I have a question. This is on the right of your screen.
Okay.
Technical, just F5.
F5. There was a question.
Yeah, you were saying economic cost functions. Do you have any experience with the difference or maybe formulated in a different way? Is it worthwhile to put the economic cost function in the dynamic optimization problem, or would you say it makes sense to cascade it and use the stationary part of the MPC, solve the economic problem, and then use the MPC to move the process there? Do you have any experience? Which one is better? I mean, for batch it's obvious, but...
Yeah. So with the people that I talked to, it seems that in practice the cascaded approach is probably a better. That means that you solve some steady state optimization first, and then you have an MPC to get you there. And the reason is because for stationary large-scale processes, most of the time they run at some kind of steady state, or that's where you make the profit. It's just you have some transients where you need to satisfy constraints. So so for these processes, it makes sense to have like a two-step, that you have like an economic optimizer, and then you have a MPC or controller that gets you there. Maybe the other advantage of that is that you have like a possibility for a human to interact, so you can see what is being proposed by the economic optimizer before you just let the MPC loose. Yeah.
I have another question.
Yeah.
You said that the main reason why mainly linear MPC is used is speed. But one difference between linear and nonlinear solvers is also that linear ones can find global optima, but for nonlinear this is difficult.
Yeah.
Is this an issue in practice?
I would say it depends. Depends on your model. So I think for a good engineer, maybe it's not an issue in practice. But if you start modeling something where you need a global optima, say and you don't simplify it enough, so you have you need some thermodynamic calculations. You need to minimize the Gibbs energy. Then it might be a problem. Yeah.
May I also comment on this question?
Please.
I don't think it's a matter of global versus local optimization. The reason why linear MPC has been used and is still 95% of the cases used is that you get linear models from data rather than having to write down your linear differential equations, having lots of parameters which you don't know which will change over time. So that, I mean, if we had an easy way of getting linear models from data, which could be used in linear MPC implementations, I think the percentage of nonlinear MPC would increase independently of having global optimization guarantees or not. I think that's the main reason. At least that's from my experience. And I mean, I don't know if you agree or not.
I agree fully.
With that comment.
Yeah.
And I was also about to ask you another question that you didn't touch, or maybe you will touch later. In nonlinear MPC, you said that we can have models in continuous time as well as or models in discrete time. But I would say most of the times we do have continuous time models. What if we write down mass and energy balances, etc. So also integration is part. Time integration of the model is part of the optimization issues that we have to face. So significant amount of time is actually used not just for optimizing, but also to simultaneously integrate the differential equations. I don't know if you're going to touch that or or not.
No, that is true. We will not touch it explicitly, but implicitly in the speeding up it is there. So because these optimizers that we use, be it linear or nonlinear, they always assume that you have a finite dimensional state. So you can only have like a finite number of variables. So then you need to discretize it anyway. And this discretization will also cost you time, computation. So to avoid so this in this basic MPC framework, first we estimate the state, or we get the state. Then we begin the calculations. After we have finished the calculations, which include the integration of the model and finding the optimal trajectory for the inputs. So that could be like delta t comp. And then when we have that, then we can put the input into the plant, and then we wait for the next one. So if that is like the basic or simple MPC, and if it takes a long time to compute, then we will have some computational delay there. So this calculation here can take time, especially if you have nonlinear systems that are large, nonlinear, and then even more if you want to do robust MPC. So that can take a lot of time. So people have been working on different approaches for dealing with this to reduce the time so that you don't act on outdated information. And then, so that one approach is to make use of the sampling time. So while you're kind of waiting for the next measurement to come, you use that time sensibly, or to exploit the structure of the system, or even to replace the MPC calculation at all by, for example, approximating the optimal solution using neural networks. And we have also seen several contributions here at this conference. Yeah, Miro?
Can I just ask, how serious is this issue of this non-zero computational time from the practical point of view? So you get instability or?
Yeah.
Okay.
It depends on how big it is,
Yeah.
but you can get instability. So so like Algova, I think they showed that a while ago, that you get instability. Or you just act too late. You know, it's like if you drive your car and you want to go around the corner, you need to predict how the corner is going. If you brake too late, yeah. So we will show a bit about like computing in between sample times, some approaches, and then we will spend also some time on doing these offline policies where you avoid solving the MPC problem online at all. So we'll present some of that here. So the idea is, in that time between the sample times, is there some approximation or something simpler that we can do that is faster? And so it has been proposed there to use the sensitivity, how the optimal solution changes. And there's two approaches that are quite similar. That's this advanced step MPC and also real-time iterations. So we'll touch into them. But first, what is the sensitivity, or what is sensitivity? So the key observation that we have here is that this MPC problem that we solve at every time step is the same problem. It doesn't change. So the only thing that changes from one iteration to the next is where am I? Where's the state? So that's just, it's parametric in that starting point. So what you could do is you could examine how does the optimal solution change when the state changes. So this here would be like solutions of the full nonlinear problem if you solve the NLP, but you can approximate that using a line. So you can do this linear approximation, and you can see that if you have a small difference in p, then they can be quite close together, and maybe that's good enough. Sometimes doing something that is approximately right fast is better than waiting a long time and then doing it perfect. And often this sensitivity here is much faster to compute than to compute the full NLP problem. So what researchers have found is that the solution is actually like the solution of the NLP is an implicit function of the parameter, and so you can use this implicit function theorem on the KKT conditions, and you find that if you have a nice situation like here, where this is your parameter and this is your solution, so you see if you're here at this parameter, then the change in the parameter can be found very simply by solving a linear system of equations. There are some conditions that you have. You cannot have any active set changes, and you need some second order conditions to be satisfied then. But then if that is the case, you can set up the Lagrangian and the optimality conditions for the optimization problem, and then you can end up with a linear equation that is very fast to solve. So this can be done very quickly. If you are in a different situation, like here, that your process is at this kink, and you can have active set changes, so you have it is not so nice. You have basically two different derivatives in different directions. So in this case, you can still find sensitivities under some conditions, but they can be found then by solving a quadratic problem, a QP. And this QP is based on the KKT conditions. So, and it also can be solved, or sometimes it may be solved faster than the NLP. And then you can get the approximation of the solution. And if you can get this approximation of the solution, then what you can do is you can employ it in this what has been known as the advanced step NMPC, where the idea is really you want to reduce the the computational time. And so after we put our input into our process at time 0, then we use the model that we have to predict where we're going to be in one sample time. And then after we have predicted, then we solve the NLP for this estimate here. Yeah. So we solve the NLP for the next starting point. So that's why it's called advanced step. And then once, if our model is not completely off, once our true step has evolved to that point, what we do then is we just update the, we use the sensitivity to move the solution to the next point, and then we iterate. And we keep doing that again. So in closed loop, that will look something like this. So I'm here right now. I have pre-computed this input from before. I put that in the plant right now, and now I have time to wait until the next sample time. So I predict where I'm going to be, and then I wait for the process to actually end up there. And I use this time here to calculate, while I'm waiting, I use this time here to calculate the future and to find the next input. So this is the predicted. I'm still here, sitting here. Then the process starts to move. It moves close to where I predicted, but it's not very far away. So then what I do is I use sensitivity to adapt it, and then I quickly implement the next one. And I predict the next step, and then I start solving from here. And that has been doing over and over again. So this was proposed by Zavala and Bigler in 2009, this approach. And so by doing that, you can solve large optimization problems, but you have like very little computational delay. Yeah. So here I just have some results here for CSTR. So we have with two states. So here we have the set point in black that we are trying to track. And we have different flavors. So the blue one is the ideal one that we want to track. And this advanced step MPC, that's the one that is just solving this linear system without any active constraint changes. So it cannot take active constraint changes into account. So you see at some points here, it kind of goes far away from the ideal one, from the blue one that we want to, where we want to be. And that's because active constraints, the sensitivity information that we have is wrong. But if we solve the QP, that is the purple one, then we see that we can actually track the ideal MPC problem very closely, but we have negligible delay. So there's a similar approach that actually has been proposed 7 years earlier by Deal and Bock and that school, and that is using the same ideas or the same concept of sensitivity. And they actually even take it a step further, and they say, why do we bother about solving an NLP at all? Let's not solve any NLP at all. Let's just do like one sensitivity step after the other. So their approach has three main steps. So they put the input into the plant, and then they shift to the next solution or predict the next solution. And then from the next solution, they prepare for this next solution. And they, by formulating a QP, the same QP that I showed earlier, and they actually prepare it for solving. So they can do some pre-solve and prepare everything that it's ready to solve. And then when the measurement at TK1 comes, then they do they solve the QP, which can be done in one iteration, and then they compute the next point. So by doing that, they and then they just repeat. So by doing that, the sampling time difference will only be like the time that they need to solve the QP. So they can do that very fast. But maybe you will need some special safety measure if like large disturbance happen. So in the advanced step MPC, you will still solve the NLP, which in a way can put you back on track. If you get lost here, you'll just keep getting lost. But so it can also be considered as a special case for time varying MPC. So there's some literature on that. But in flavor, like in the idea, these are very similar: the real-time iterations and the advanced step MPC. So if you want to reduce the computational time. So this is how it looks like when you implement time TK. So here, this is what they call the feedback time. That is when you solve the QP, and then here in the preparation part, they build the QP and pre-solve it, so that when they get the new measurement, the new input can be implemented just after a very short delay. And what actually happens there is shown here. So we start at this point here. So then at the first iteration, it goes to this point. At the second, it goes to here, and then here. So we don't track the optimal solution perfectly, but we get close enough. And in control, often doing the right thing or doing something approximately right fast is better than to do the perfect thing after a long time. Miro, yeah?
If we solve, for example, differential equation, then we have a predictor step, and then we have corrector step.
Mm-hmm.
That should bring us somehow to this nominal trajectory. So is there any similar mechanism here?
Yes. I didn't mention this, but this sensitivity QP, the QP that you set up, you can modify that slightly, or you can do some tricks there slightly. That's also described in these papers by Deal, that it actually does a predictor and corrector step in one. So it is combined with like an SQP step. So it becomes a predictor corrector QP. That will then not just give you the tangent, it will also get you closer.
But that doesn't help you with flat model mismatch, right?
No.
So that's probably the reason for the advanced step.
Yeah, or a big disturbance that comes in, you'll get lost.
Yeah.
So that's why, yeah. Okay, so the takeaway for this first part is that we want to minimize the delay between the getting the new measurement and the input, and and the time between the sample times, you can use that to prepare for the next sample so that you're ready and you can implement it right away. Because delay is the worst thing that you can have when you do feedback control. So, but computers and algorithms and hardwares, they get better and better. So we can solve bigger and bigger problems. So for standard MPC problems, even if they're linear, you can nonlinear. It might not be such a big problem, but once you want to take uncertainty into account, there's many different possibilities, and then the formulations increase rapidly in complexity. So that's why maybe these approaches can still be useful there. So the second approach then is to just say, I don't want to do any online computations at all. I will not solve any optimization problems, and I just take everything offline.
Just ask one question on the online thing before you move to the...
Okay.
Do you have any experience on doing something even simpler, just loosening the tolerance. Say, okay, I just call F-min corner IP opt with a very slack tolerance and use that in feedback. So it will give me an answer fairly quickly. Of course, it will be a highly suboptimal, or I mean, possibly highly suboptimal solution, but I keep doing that in feedback at a very fast sampling rate. Do you have any experience on that? Is there any literature focused on that thing, or?
Yeah, there is. Yeah, so Rado said we can do what we want. So no, there is literature on this, like inexact solves. So if you have inexact solves for the model, I have not myself looked into that any closer. There's also, I don't know, maybe I can ask back. Like if you have, as you mentioned, you need to integrate the model in time. So one could also conceive that, like when you start your iterations and you're far from the optimal, that you just kind of have a sloppy integration tolerance and then you tighten it when you get to the solution. Has there been anything about that? I don't know. But there is literature. I don't know. Maybe you have been involved in some of that. I think maybe.
I've been doing something on stability for suboptimal MPC, so that's somehow related.
Yeah.
As long as you keep not doing worse of the warm start. So if you warm start your solver and you stop at a point where the solution is no worse than the warm start, at least you have nominal stability guarantee.
Okay. Yeah.
But I'm more interested, rather than theoretical guarantees, I'm more interested in how good the solution is in feedback and how it compares with RTI or advanced step approaches.
Yeah, that maybe we can just give that to the PhD students here. That I think there's definitely something to look for there. There's definitely something to find. So now everyone will take over, and
That mic.
the mic.
Just get clipped on. Okay. Can everyone hear me okay, or should I use the microphone? People at the back? Fine, okay. Warm then. Yeah, okay, fine. So I'll be talking about potentially moving the MPC offline and looking at explicit MPC strategies, both traditional ones and also some more recent machine learning approaches that have been suggested. So the essential idea behind explicit MPC is for the original classical solution is for a linear MPC problem where, as Johannes said, the MPC problem is parametric in X. But for a linear MPC, it's a parametric QP in X. And it has some special structure, namely it is piecewise linear defined on polyhedral regions. And by that, I just mean that there's a matrix K times X plus C1 if X is in some region R1. And you just have to find all of the regions in all of these matrices K and vector C to find what your optimal input is going to be. So this explicit control law can be computed offline. And I'm not going to go into the exact details of how it would be computed, but the essential idea is that if you're in a certain region, then you can go find that, okay, the optimal K and C for this region is, you can find from a point, and then you can find the boundaries of this region because the active sets, you can find the points at which the active set is going to change, and then you just go around your state space and find a new region where you have a new constant K and C, and then you find a new region, and you so on, just repeatedly span your state space out. So that's the essential idea, and there was, I think, recently, yesterday, a talk on an extension to MPT Toolbox to go and do explicit MPC also for tube-based MPC. So there's lots of existing solutions on tools that make it easy to go find these explicit control laws. So the online situation is that you have to determine which region you're in, and then you have to evaluate this affine policy. And often, evaluating the affine policy can be very cheap, but determining which region you're in can be expensive. And the essential idea is that the number of regions is exponential in your horizon N, as well as in your state dimension X. So So this is just an example from the paper by Bemperod, where they just increase, it's the same system, but they're just increasing the horizon length, and very rapidly you end up with a very complicated explicit control law, where you have, I think in this case, it's over 40 regions for a relatively short horizon. This means that it's both more expensive to solve the original explicit MPC problem, but it's also then more complicated to implement your explicit MPC solution. And there's various extensions on this to sacrifice your optimality to have less partitions. I'm not going to go into them, but the references are below. But there's also some other approaches where people say that the explicit MPC solution just in general is unappealing. And considering that we have him here, because he's giving the keynote tomorrow, I pulled a quote from his paper from 2007, where he says that from a purely theoretical point, the explicit MPC is unappealing, as it replaces a polynomial time method for solving the MPC with a method that is not polynomial. And practically speaking, also the offline computation becomes more difficult when you have a longer horizon or increased dimension of your problem. And yeah, I don't know if you have any comments on that or similar view to now, but that is essentially the challenge of traditional explicit MPC, I think. So there's been some recent work on, or not even recent actually, on ideas of replacing the online MPC problem by an offline neural network optimization. And to my knowledge, the earliest reference of this is from 1995 by Perosini and Zappoli, where they essentially do what is still kind of being proposed, but with less safeguards, that they go and solve the MPC problem at many states in the state space X, and they get a collection of matrices that are the X matrices and the corresponding control input at the first time step, and then they try to go train a neural network to minimize the loss between the MPC solution U and the neural network output. Much more recently, Karg and Lucia showed that the neural networks can exactly represent this piecewise affine control law and do so at a significantly less computational cost. So the cost of representing both in memory the explicit MPC law is the cost of representing the explicit MPC law's regions and matrices K is more than storing the neural network parameters theta. And the cost of actually finding the region and just evaluating your neural network forward is also more. So more generally, you can't find an exact representation. And indeed, for this work, they had to rely on some assumption that you knew some properties of the piecewise affine law to be able to construct this exact approximation. So more generally, what you're kind of relying on is that neural networks can represent continuous functions that are defined on a complex set to an arbitrarily small tolerance. And you're going to make some approximation error. However, you also know that nominal MPC is inherently robust. And what you can think of is that this approximation error is just a bounded disturbance on what your optimal MPC should be doing. And when you approximate it by a neural network, it's eating into this inherent robustness margin of your nominal MPC. So even if you don't get the exact solution captured correctly, because your nominal MPC solution is inherently robust to small bounded errors, your approximate solution is still stabilizing for your system. Okay. So there's an important caveat over here is that if you're replacing model predictive control laws by neural networks, then your model predictive control law has to be a continuous function. If it's not a continuous function, you can't replace them and guarantee that you're going to do this to a low tolerance. So on that note, you can take a step back and say, well, when does a model predictive control problem define a state continuous feedback policy? And I'm not talking about it being continuous in time, because we're expecting a kind of stepwise input, that's okay. But that if you perturb your system slightly, that the input that your model predictive control is going to give you should also only be perturbed slightly. So if you just consider it as a general nonlinear optimization problem, where you're trying to minimize some v, where u is your optimization variable and x is the parameter, and u has to fall into some constraint set u of x, then what does it take for the solution of this optimization problem to be discontinuous? You need either to have multiple solutions. That's just because when you solve it from different points, you might end up at different solutions. Or you need this constraint set u of x to be discontinuous. If one of these two hold, then you might have a discontinuous control policy. So in the MPC framework, that means that you need to have two conditions that hold. You either have to have, you need to have a unique optimum, and also along with this some bounded constraints at u, and you have to either have a continuous system with no state constraints, or a linear MPC with polyhedral state control constraint sets, and these are sufficient conditions to ensure that you have a continuous MPC solution. Which, yeah, for linear MPC, that's fine. This is the normal scenario for linear MPC, and we know that linear MPC is going to be piecewise affine on polyhedral sets, so of course you could approximate over neural networks. But for a more general nonlinear system with state constraints, it's a more difficult question to answer if you can even try to do this. So just a very quick example, the classic example of a discontinuous control law, I think, is this example here, where you're trying to regulate this one-state system to the origin, and you have one input u, and you have that the first state evolves with x1k plus u, sorry, there should be an index k over here, and x2k plus u cubed, and you require that after a horizon of 3, you're at the origin. Well, this controller that stabilizes this problem has to be discontinuous. And you can see this because in the quadrant with a positive x1 and positive x2, you need a negative control input u, while when you have a negative x1 and x2, you need a positive control output u. So you need a negative input in one quadrant, a positive input in another quadrant, and you can only have a 0 input when x1 and x2 are at the origin. So because of that, if you're just going around in a unit circle, like shown over here, your control input has to jump over 0 to stabilize the system. So this is showing if you just have a unit circle, so x is cos theta sine theta, and you're moving x around in this circle, then as you go from minus pi theta to pi, your optimal control input when you solve this problem is completely discontinuous. And yeah, you have to have a discontinuous control. But this is a quite extreme case, I think. Yeah. And it's entirely a problem, in this case, of your nonlinear model, the structure of having this u and u cubed inputs that are tied together for the two states. To give a second example, this is about the non-uniqueness. Again, a very, very simple. Here, your control horizon's 1. You just want to regulate from your starting point to the origin, and your state's going to evolve by x naught squared minus u naught squared. So it has an obvious solution. U star of x can be plus minus x. That's fine. But because it's non-unique, that means it admits a continuous and a non-continuous control policy. So if you are just generating a bunch of data to go train your machine learning method, you could accidentally generate on either one of these non-unique lines. So this can be shown in a picture. So here, we just solve this problem. We randomly initialize IPOPT. We try to go solve it. We generate training data. And most of the training data ended up being on this u equals x line. Some of it, this dot, those 3 dots over there, ended up being on the u equals minus x line. Now, if you try to go train your neural network just in imitation learning on this naively, you're going to have a perfect 0 loss. Everything looks good on your optimization. Everything's happy. But, I mean, you don't want this blue line to be your control policy. It's not great, let's say, for the very least. So this kind of non-uniqueness can actually lead to some serious problems because, in general, it might not be that easily detectable, especially if you're trying to solve a big system and you are solving it in parallel, so you're not necessarily able to warm start it from a previous solution. You might be running in different areas of your state space in parallel, and you don't know that you're on one branch and that branch is going to disappear, or that another solution's on a, what's the word I want to say, separate branch of your solution trajectories. So technically speaking, if we have soft constraints, which, as Johannes mentioned, soft state constraints, then you should not have example 1 unless your system is, I want to say, silly. So the reason why example 1 gives you the problem is that you have a combination of this state constraint that you have to be in the terminal region, which is sensible, and you have this odd dynamics where your behavior of your two states is linked by this U and a cubic U. Unless you have like a weird dynamics that require a non-continuous control policy to stabilize your system, then otherwise, if you don't have soft constraints, you should have, at worst, example 2, where you have this continuous and non-continuous policies that are able to stabilize your system. And I don't know, you're free to correct me over here, but I think that if you were designing a plant or designing a control system, if you were doing so, you would want as far as possible not to have the case of example 1, where just to stabilize your system, you need to go arbitrarily change your, let's say, actuator valve by a huge amount instantly, depending on where your state is. That seems like a very, problematic system to try to control. So what I'm essentially trying to say from this imitation learning perspective is that neural networks can represent control policies, but just training them doesn't necessarily lead to good closed-loop performance. And a key issue is part of your selection of your training set. What you want to do is you want to select your training set to be based on closed-loop trajectories in the operating regime you're interested in, specifically the closed-loop trajectory that you would get if you were to use your approximate control policy. This is the only way to guarantee that every state that your control policy might come across, it is seen during its optimization. And that's a bit of a challenging problem to guarantee. But there are two very, very different approaches that have been recently proposed. One for Kumar, Rawlings, and Wright was for very large-scale model predictive control. I think they considered distillation column over here, where really picking good operating regimes and being very efficient with your data was necessary due to the sheer size of your system. And then another completely different approach by the Paulson and Mesbah group, where they're leaning heavily into like a machine learning approach to go finding these critical trajectories that you have to learn. But also more importantly, even if you have trained it entirely, you have to verify your performance by considering closed-loop trajectories of your controller. That is necessary. You have to probably have to sample heavily, and you're going to have to find this. And again, there are many different ways that this has been proposed for this to be done. And I'm just going to go into slight detail of this one that's been proposed by Hertnack et al. Because it's, I think, relatively popular in terms of the imitation learning framework. It's the kind of most common verification method that I've seen, at least. And it's a validation based on something called Hoeffding's inequality. So the basic idea is that you want to verify that something holds. So you define an indicator function of the thing that you want to verify. In the case of their original paper, they said that they would want an indicator function that's 1 if the difference between your MPC solution and your neural network solution is less than some parameter eta, so the deviation between the two, and 0 otherwise. Then you select a critical value and a confidence value, because what you're going to verify is that the probability that your indicator function is 1 along a trajectory that you randomly sample will be, this probability is greater than your critical value mu, and that this inequality will hold with confidence level 1 minus sigma h. So you've got 2 layers of a probability constraint. You're verifying that a probabilistic constraint will hold 1 minus sigma h. And it's relatively simple. It's based on averaging and sampling your space. You randomly sample your space and calculate the average mu that you observe when you actually deploy your indicator function over your state space. So that's quite simple. Then if this inequality holds for a given number of samples p, then this inequality is satisfied with at least a confidence level 1 minus sigma h. Sorry. So important things to observe here. You cannot set mu crit to 1. If you do, this inequality will never hold. You also, as you try to go tighten delta h, you get a rapidly expanding amount of samples that you have to take. So this is only good if you want to say, I want this probability to be satisfied with probability. I want this to be satisfied at 95% probability 95% of the time. Then you end up with a reasonable number of samples. By that I mean probably about somewhere in the region of 300 to 1,000 samples you'll have to take. So if you want a very, very rough guarantee of feasibility, as you tighten this, you start requiring exponentially more. And again, this is very expensive because you have to solve the full MPC problem in closed loop along the trajectory that is defined by starting with your neural network at that point and then check whether it's going to, obey this bound. So it's quite expensive. I'm sorry. And you can swap this out for a cheaper metric, for example, constraint satisfaction. But you can satisfy your constraints and still have quite a significant degree of suboptimality. So 2 issues with this verification, but it is quite common to see this used in the literature.
Everyone, sorry, maybe I lost you. What is the capital T? What am I sampling?
Okay, sorry. T is a trajectory. So you start off at some initial space in your region that you're interested in, then you
Trajectory of what?
trajectory of your state. So it's the x0, x1, x2, x3, x4 until you reach your terminal region or your yeah. So you have to satisfy until you reach the terminal region or until you reach your set point or whatever you define your problem as. Yes? Sorry?
Does it make any difference whether the closed loop trajectory is originated by the actual MPC controller or the neural network approximation?
Yeah, it has to be the neural network approximation because otherwise, if you have an epsilon difference in your states and you go to somewhere different, then you have to verify that you go into somewhere that your MPC wouldn't normally go to, but if you are going to go there, is the difference between them still large or still small? Yeah. So it's the trajectory generated by your neural network, and you have to check at every point on that trajectory if this bound holds, or if some other bound holds.
I'm a bit surprised that neither the state dimension nor the input dimension is playing any
Okay.
role in this
So
qualities.
this is an interesting point, and it's weird but true. So this is somehow relying on this law of large numbers and kind of Monte Carlo sampling thing, where you can show that you have like a very bad coefficient, but as long as it's independent of your state dimension to evaluate an integral, it just grows with, your accuracy grows with what's its square root 1 over n for a Monte Carlo estimate of your integral, and that ends up being the same expression that you get over here, that when you're trying to increase your accuracy, it's related to the square root of your number of samples. So it relies on a similar kind of law of large numbers behavior, where it's independent of a state dimension with a huge constant at the beginning of that independence.
So that constant is a function of the state dimension?
Yeah. That function is, I'm not entirely certain about that. Yeah, the increase in accuracy isn't a function, but maybe the original accuracy is. Yeah. It also says nothing about the tightness of this bound. It's a completely loose bound. It's maybe something about, you can think of it as a concentration kind of thing from statistics. But yeah, it doesn't involve your state dimension of your underlying system trajectory, NX. And that's the original reason why they proposed using it, is because theoretically at least, it's good. Okay. So just taking some steps back and to give a bit of perspective on this, the reason why you have bad behavior is that you separated your MPC problem from your neural network training problem. And you might wonder if these problems could be combined, that you somehow embed a neural network in your MPC problem to get a somewhat better behaved approximator. So what would happen if you do this completely naively? That is, at each x0, you try to go solve this dynamic optimization problem where you have a neural network that's going to go give you your output UK, where the neural network takes in a constant parameter theta and your current state of the system, and now you're minimizing not over your control actions UK, but you're minimizing over your parameters theta. Well, what you have is you are finding the optimal continuous nonlinear feedback policy, assuming you have a large enough neural network, but you also have a completely computationally intractable problem. Like you can't do that. Because at every single sample time, you have to go and train a new neural network, so not really feasible. And you also, the reason why you can't reuse this network from different sampling times is that it would only see trajectories, states along its trajectory for a certain length n. So if there's any deviation away from that trajectory, it's a completely useless controller. But there could be another idea to start making it useful, is that you find a neural network that optimizes for the performance for a considered set of states in X. So that's the idea that you're going after, to find a neural network that optimizes performance for all X that you're considering in some big set X naught. I know I'm getting close to lunchtime, but I will be done soon. Sorry. So the idea, one idea is what you could do is you could try to minimize the expectation of your MPC objective subject to some distribution that is defined on a set of your initial states. So that X naught is now being distributed by some distribution pi of X. This actual distribution doesn't matter as long as it's positive over the set X that you want to consider constructing your neural network on. And even though you never explicitly solve an MPC problem here, as the original MPC controller, if it's continuous, is optimal for this problem over here, then if your neural network gets to the optimum, it is approximating your original MPC law, even though you're not explicitly at any point solving an MPC problem. So this kind of idea is that you can construct a neural network controller offline that recovers your MPC to arbitrary precision of your objective. And you get, well, an offline state feedback controller, UK is equal to your neural network, xk of theta, which is based on some work that me and my supervisor did last year and this year. And again, you can show that if you're using a ReLU neural network with a linear MPC, that you can exactly recover your MPC solution if you wanted to, not solve the explicit MPC in the first place. And yeah, I've been showing this entirely with discrete, but you can, of course, have a continuous time formulation at the cost of more expensive optimization. Yeah.
So I'm not sure if I understood this correctly. So here, are we substituting the affine control law by neural network nonlinear functions, or
so a neural so a neural network with ReLU, or a neural network with a piecewise activation function defines a piecewise activation function. And this entire proof that they had to do for the ReLU approximation was basically just based on that neural network with affine activation functions define a piecewise affine function. So yeah, they're the same thing. It's just a different representation that is easier to optimize over because now you have a finite set of parameters theta. Okay. So in implementation of this, just going to go very quickly over some basic ideas here. You have to sample from this probability space x naught that you define and get some samples of x naught, your parameters, and your current neural network's parameters theta that you can then run in closed loop simulation. Now, this is closed loop simulation of your neural network and your difference equation. So you're not solving an MPC, so it's actually relatively fast just to simulate this. Then you can evaluate whatever your cost and constraints were for this provisional policy with parameters theta k, and then take this back and calculate an expectation of your cost and the gradient of that expectation. Where the idea is that as long as you do this closed loop simulation in an environment that supports automated differentiation, then you get your gradients for free. Well, for free. similarly, you can try to go incorporate your state constraints into your objective function. So then you're only trying to estimate a single expectation, the expectation of your penalized constraints j, penalized objective j, and the gradient of your penalized objective j with respect to your neural network's parameters at that iteration. But this is all done as closed loop simulation with only the neural network. So it's relatively fast, surprisingly fast, you would say. So the key choice over here is how do you sample? When do you stop sampling? How should you evaluate your expectation? And how should you actually perform this optimization? So the important thing to note here is that although there's an expectation, we're not talking about a stochastically evolving system. The expectation is just that you don't know where your initial state is, but this policy is going to get the initial state as a measurement. So it's not a question of propagating your uncertainty. You have a completely deterministic system. So just to write it out semi-explicitly, once you know your x naught and you have a theta, then the evolution of your trajectory is just given by your system dynamics. So this expectation that you're evaluating with respect to is not the propagation of the distribution at x naught to some distribution at the final time, but instead just evaluation of, well, I have this prediction of how my system would evolve, and this prediction is weighted by this probability distribution, but you're not explicitly propagating your initial distribution to the future. You just want to evaluate this multidimensional integral, which of course is a challenge in and of itself. But importantly, you don't need to get an accurate estimate of this. So if you're okay to get an inaccurate estimate and then just use a stochastic optimizer that is okay with having some noise in your estimate, then you can get, say, select some points by low discrepancy sampling of your cumulative distribution, and then use this at some iterations. And the optimization will work because all your stochastic optimizer needs is an unbiased estimate of your expectation. It doesn't need the actual expectation. However, during optimization, we have found that it's quite useful to start moving towards an accurate estimation. And you can try to get an accurate estimation by any means necessary. So you can do adaptive cubature, you can use sparse collocation, quasi-Monte Carlo methods. You kind of give a very expensive offline optimization with the expectation that you're not going to have to do this that often. So also, I didn't mention uncertainty, but if you can solve this problem over here, then also considering time invariant parametric uncertainty is the same problem, because you can augment your state vector by your uncertain parameters p and just have them not evolve in time. So it's the same kind of problem if you don't give your parameters p to your neural network. So that means that you can handle uncertainty in this kind of time invariant setting, which is analogous to multi-stage MPC, where you have a robust horizon of 1, but then afterwards your system evolves deterministically. So you have an uncertainty at your initial starting point. That kind of scenario can be easily incorporated in the same kind of expectation over here. Yeah. So just a sanity check that you can tell that things are actually working out. I'm going to show two 2D examples that we can plot and show the control laws and things. So a double integrator, it's a standard system, nothing much to say about it. We are considering a constraint on x2 and also a constraint on your input. They both have to lie between -3 and +3. And our domain of interest that we want to construct, the explicit control law, is from -9 to 9, -3 to 3. So this is what your explicit MPC solution that you get is. And this is what you get if you do what we describe with the sampling of the spaces in your state space, and then trying to start off with a bad estimate of your expectation and then get a better expectation as you go on in time. We stopped at a tolerance of, I think, 0.1, so that's not a particularly high tolerance, but yeah. So first of all, you can see there's some deviation. I can put a circle on it over here. the region where this change between these two slopes isn't exactly correctly predicted. And this can be for a variety of reasons, but we'll get into that in a little bit. But the more important thing isn't how does the policy look, it's how does the closed loop performance between the two of them look. And for that, what we can check is what is the closed loop objective value for starting at different points in your state space. So this is x1, x2. This is the logarithm of our closed loop objective value. So if we start at a certain space and we're controlling with our neural network, what does the cost look like? Well, it looks fairly well behaved in this picture. This region of mismatch doesn't actually come across when we compare what's the actual closed loop performance like. And on my left-hand side, your right-hand side, this shows the difference between the MPC closed loop costs. So when we implementing the MPC in closed loop, re-optimizing at every point, and when we're just using this optimized neural network control policy. So the first thing to say is that this is a logarithmic scale from 10 to the minus 4 to square root of 10, so that's about 3.4-ish. As you get close to your origin, your difference between the objective functions goes down. At the origin, it's 0. I just stopped the scale at 10 to the minus 4. This region where we had the mismatch, it does correspond to a slightly more inaccurate, slightly worse performance when you're down here. However, this worse performance is about, the colors are a bit different on my screen and on the slide, but about 10 to the 0, 10 to the minus 0.5, while over here that corresponds to 10 to the 2, 10 to the 1. So it's about, what is that? Less than 10% to 1%, a 10% to 1% difference in the closed loop objective when starting in that region, but it's not particularly high, especially as when you start regulating closer and closer to the origin, that difference goes down and down and down quite rapidly. Also, there are some regions where for some reason the controller is able to do very well, even though it's far from the origin. Okay, but that's a simple problem. Yeah, I spoke about that. Let me just quickly wrap this up for the lunch in 5 minutes. So in contrast, what will happen if you did the same thing with imitation learning? So what happens is that a huge amount of your state space we've marked as white because it leads to a violation of the state constraint that x2 must lie between minus 3 and 3. And the reason is that this x0 is not positive invariant. It's not a positive invariant set under both the MPC and the approximate neural network policy. It's rather just the set that we were interested in. But because when you do this embedding of the neural network, it is inherently trained along trajectories that it itself generates. It sees going out and then coming back in. Because in the double integrated system over here, you can take one step out and then step back in. So that's okay. You don't have to worry about this kind of data generation step as long as you pick a long enough control horizon when training your neural network. The second, and of course, in this region that is entirely self-constrained, the imitation learning MPC does perform very well. We gridded this with like 1,000 points for 2 dimensions, so it should perform well. Just
I'm still curious about what you just mentioned. This is what I'm thinking all the time. The problem would be, well, infeasible, or the training of the neural network will be problematic if I'm not careful with the initial sampling, right? With the sampling of the initial conditions. Right? Because well, it doesn't have to be solvable, feasible. So only in the case of double integrator, but I still don't see.
What don't you see? Sorry.
Well, you see, okay, I violate the constraint, and then I'm coming back, but then I just violate it.
No, this isn't a constraint. This is just like the state that you're interested in. So, I don't know, if you were operating a plant, you might have, I don't know, R100, a bigger number. There might be a certain operating regime that you're actually interested in making this explicit controller for. That was the kind of scenario we were going for. We're just doing it in 2D to show. But in that operating regime you pick is probably not positive invariant. You probably are going to leave it, but you're going to come back to it. So if you have that kind of situation, you can't have that for imitation learning. You have to find a set that your imitation learning neural network will never leave. But it's okay to do it if you embed the problem because you're going to be training along trajectories of that problem. That's all that I try to make a point of.
Of course, what I'm asking is even bigger. Well, it goes beyond. It's a standard question in MPC. So yeah.
Yeah, but I wasn't. Yeah, it's not. It's respecting the constraint on x2. There's no constraint on x1. It's just the double integrated velocity position. Yeah, you're constraining velocity, not the position. Yeah. So, just a slightly different example. This is a nonlinear system. It's a compressor that you're trying to avoid surge control over. I'm not going to really go into the details behind it, just say that it's two states. You've got a penalty if x2 is below 0.4. This is just to try to promote good behavior because your compressor shouldn't operate when it's below this range. And it's weighted as so. These are not things we decided. It's directly from the MPC problem over here because you can't enforce this constraint over here. So we took their problem, we're just doing it now because it has an interesting solution. So if you have a nominal MPC policy, it looks like this. So one thing that's different is now we're saying that there's two parameters, gamma and beta, that are uncertain and normally distributed. So the pink lines are showing the nominal system, where your nominal MPC is expecting to have, and it regulates it to the set point over there. And the dashed lines are some draws from your uncertain parameters. Okay, so it's a small deviation. Your MPC is still able to stabilize it. Everything works fine. But we can solve this problem if we go into this framework of constant parametric uncertainty and see what does the neural network do. So it's not getting the parameter as an input again, it's just getting the state as an input. So the neural network policy is completely different. It is nearly not a function of x2. It is just a function of x1, and it's nearly linear. And this was somewhat expected because in this original paper, they are trying to do this in a robust manner. And what they were able to show in this paper is that a linear controller was enough to stabilize the system. That's what they showed analytically when they were looking at it. So this kind of behavior is interesting because you explicitly asked for a minimization of the expectation, and it found, okay, the state x2 doesn't matter then. I should only consider something in x1, which is, I think, an interesting result. The trajectories are more or less the same, apart from this region when you start getting close to the objective. You can see that the curves that it makes for the uncertain system, the dashed lines, are slightly different. There's, I think, quite a large loop over here. And then again, when you're starting over here, the nominal MPC takes you all the way nearly to 0.54, I think, while the neural network policy keeps you about 0.5 and then takes you in. So there is differences in the trajectories that it's doing. We can then look at this in terms of the average closed loop performance. So this is the expectation of your closed loop when you implement your neural network policy. It looks relatively well behaved. You're going from regions of high cost to region of low cost, and you stay within this region of low cost at the end. So it finds a steady state set point close to the set point that you desired that kind of balances it for all the uncertainties you're considering. But there's offset. We can then compare this to the nominal MPC policy for the same system. And the lines are jagged because taking the expectation of an MPC solution that has to be calculated in closed loop is expensive. So, and I was doing this on a laptop, so I did not do it to the same degree of accuracy as the right-hand side. But the essential picture is roughly what you would expect, that when you start off far away from your set point, both the nominal MPC and the neural network policy are doing what they're meant to do, take you close to your objective. The difference is that when you get close to your objective, because your nominal MPC did not account for this kind of uncertainty, it takes the uncertain system to potentially bad set points, which is why this region near the set point is actually the worst, where there's a 60% relative difference between what your MPC finds and what the neural network finds in the end. So if you were actually interested in your expected performance, maybe because you're doing an economic situation, then it would make a big difference to just include this kind of simple uncertainty structure in your problem. Okay. There are other proposed neural network embedding approaches. We were not the only one. Some people here might know Druronia. It's Druronia and Druronia Vrabi, I think, are the main two that worked on this idea. And also Lee et al. Did another version of this. So these two approaches are very similar to each other. They both try to do their validation by that Hoofding inequality that I showed you. Here, optimization is entirely preceded by random sampling. Here, they rely on random sampling, but also a two-stage stochastic program where they try to go find the most important uncertain parameters to consider. Well, what we did, if it wasn't clear because I was going quite fast, you're doing stochastic optimization with adaptive sampling. So you're deciding based on what your neural network policies currently are, what are the most useful states to consider, at least for the next few iterations, and then redo it again and again and again. Yeah, so that's the main difference. But all three of these ideas all rely on embedding your neural network in your optimization to get better closed-loop performance as you go forward. So the takeaway from our section, or in this section at least, is that neural networks can represent MPC policies with some restrictions. You can do imitation learning. It's simple to implement, difficult to guarantee. You can do embedded optimization, which is a harder implementational problem. That's a misspelling of implementation, but okay, it's a harder optimization and implementation. It can handle uncertainties of a certain form, and it has built-in guarantees. Yeah, you can, I haven't really gone into that, but if you want to go guarantee your constraints to a certain probability, you can incorporate that in the stochastic optimization framework, and as long as you're using an appropriate optimizer, then that will be handled by the optimizer. So you don't have to do this separate validation step at the end. But yeah, that is all we have to say for this part of the workshop. It's now 3 minutes over from lunchtime, so thank you all for staying, and we'll continue with robust MPC afterwards.
Some quick appetizer for the afternoon that we are going to cover.
Yeah, afternoon we will look at some different robust or some selected robust formulations for MPC that have been proposed in the literature.